After a long gap, welcome back to this series on RTL modeling using Verilog. In the previous session, you were introduced to the idea of behavioral modeling using HDLs. We saw that different behavioral models of hardware can be written using what is called sequential statements. These sequential statements enable us to specify different conditions in some stated order. And these sequential statements are written using the always block. The previous session served as an introduction to the always block, which is used for behavioral modeling. So after watching the previous video, I presume that you have some fair idea of the use of sequential statements. Please remember that the term sequential in the phrase sequential statement is intended to convey the idea that this family of statements is used for specifying different conditions in some sequential order. It has nothing to do with sequential circuits. Of course, we can use sequential statements for modeling sequential circuits also. But in this context, the word sequential is used to mean that the statements are used for specifying different conditions in some order, in some sequence. Okay, in this video, we are going to examine the modeling of combinational subsystems in greater detail. Of course, we all know what a combinational circuit is all about. The definition of combinational circuits is normally introduced in any 101 course in digital design. So we know that the combinational circuit responds to the present combination of inputs. The combinational circuit responds to the present combination of its inputs, which means the output of a combinational circuit depends only on the present combination of the inputs. The output depends, or the output is a function. The output is a function of only the present combination of the inputs. I mean, it is equivalent to stating that combinational circuits always live in the present. Combinational circuits always live in the present. They are unconcerned about the past. Of course, we will examine this aspect of combinational circuit in greater detail when we study sequential circuits. Combinational circuits form an integral part of any digital system. The actual role played by the combinational circuits will become more evident when we take up sequential circuits. For the time being, we will treat combinational blocks in isolation. We will focus more on the modeling of different typical combinational subsystems like multiplexers, decoders, arithmetic circuits, uh, then priority encoders, and so forth. So, as we have seen earlier, combinational circuits are modeled The behavioral model of combinational circuits is written using sequential statements inside an always loop. To illustrate how combinational circuits are modeled, we will start with one of the simplest combinational subsystems that you can think of, that is the 2:1 multiplex. Of course, you all know the structure of the 2:1 multiplexer. It is very simple. You have two inputs, I0 and I1, which are selected based on the state of a select input. And depending on the value of the select input, either I0 or I1 is connected to the output. So we will try to model this subsystem. We start with the module definition. So we have module mux 2:1. It is always better to give some meaningful names to the modules. We have the inputs select I1 and I0 and the single output Y. Then we have the declarative part where the port directions are declared. We have the inputs comprising of the select I1 and I0 lines, and we have the output which is just a single line, that is Y. Of course, you can see that I have declared the output to be of a reg signal type. It must be kept in mind that whenever we are assigning a signal inside an always block, it has to be declared to be of type reg. There you go. That is the declarative part of the code. Now we will move on to the functional part of the code where the behavior is specified. We use an always block. We must include all the inputs in the sensitivity list of the always block. Include all inputs. So why do we insist on including all the inputs of the combinational circuit inside the sensitivity list? It's good coding practice. Why is it a good coding practice? It is because by including all the inputs of the combinational subsystem inside the sensitivity list, we ensure that the simulation behavior of the circuit is always consistent. The behavioral simulation and the post synthesis simulation are always matching with each other. If we don't do this, that is, if we don't include all the signals in the sensitivity list, then there is no guarantee that the behavioral simulation and post synthesis simulation will match. So this is a very important coding practice as far as combinational circuits are concerned. There is one more very important best practice which we will see later. Okay, so now we will move to the operative part of the code. It is just a single if statement which depends only on the select input. So if the select is 1, we assign the output to I1, else we assign the output to I0. It is as simple as that. We are done with modeling the 2:1 mux. So we have completed our first assignment, that is modeling a simple combinational subsystem. Of course, it is not that we are doing this for the first time. We did model some combinational blocks in the previous session also. But from now, we will be focusing on modeling different typical combinational building blocks or combinational subsystems. So moving forward, we will take up another combinational block, which is going to be again a multiplexer. This time it is the 4:1 multiplexer. 4:1 mux. So we all know how a 4 to 1 mux looks like. As the name implies, there are 4 inputs: I0, I1, I2, I3, corresponding to the values of the select line 0, 1, 2, and 3 respectively. And the select line is a 2-bit select line. So that's it. Now we will try modeling the behavior of this multiplexer. I am dispensing with the module definition because I am presuming that by this time you would have already understood how to define the module and declare the inputs. So right away we will go to the always block. The first step being to include all the input signals in the sensitivity list. This is a good coding practice, as I mentioned. Always at I1 or I2 or I3, I0, I1, I2 or I3, or select. So here we have considered the input lines as I0, I1, I2, I3. Alternately, you can declare the input I as a 4-bit vector. Okay, now coming to the description of the behavior, we all know that it's an if then else template, but for this circuit we will try to model it slightly differently, because this 4 to 1 mux is a good candidate for the case statement. So here we will model this behavior using a case statement. We can use a case statement whenever there are different conditions to be specified based on a single based on the value of a single line. In this case, the single line happens to be the select line. So when the select line happens to be 0, you assign the output to I0. When it happens to be 1, you assign the output to I1. When the select line is 1, 0 or 2, the output is assigned to I2. And for 1, 1, the input I3 is selected for being connected to the output. Now, you can also include a default case. That means if none of the previous conditions are valid, then you can specify some default case. This is not really mandatory, but there may be compilers where they insist on uh, providing a default statement for a case block. You close the case with an end case statement, and then of course you wrap up the always block with an end statement. Of course, then you also will have the end module, which I have not shown. So there you are. This is the model for Verilog model for a 4 to 1 mux. Of course, naturally the question will arise, can we use an if then else block for describing this multiplexer? It is acceptable. You can also use an if then else block. And from the synthesis point of view, the if then else block will synthesize into the same module as the case statement if all the conditions are non-overlapping, which means a case and if are equivalent if all conditions are non-overlapping. In fact, we can use the case statement only when the conditions are non-overlapping, because if the conditions happen to be overlapping, then the question of priority will arise. After all, we are talking about sequential statements. So the question of which condition is to be given higher priority, that question will arise. Therefore, naturally, we cannot use the case statement, because the case statement, all the statements are treated concurrently. Hence, in the case of overlapping statements or overlapping conditions, we will use if then else blocks. In fact, for these two cases, the hardware that is synthesized will also differ, because if the conditions are non-overlapping, we will have concurrent hardware. That means all the blocks will be at the same level. Whereas if overlapping conditions are present where priority is specified, then you will have a multi-level synthesis. So anyway, we will have a detailed discussion on this later. But for the time being, for non-overlapping case, the hardware that is synthesized will look something like this. All the blocks at the same level. Whereas if we are considering a if then else kind of behavior, then it will be a multi-level hardware. So one key takeaway here is that we have to be very discreet, very choosy while using if then else statement, because the more the number of branches in the if then else block, the larger will be the delay. Of course, we will examine all these nitty-gritties of synthesis in some of the later sessions. Okay. The next module that logically will follow is the decoder. We all know that the decoder is the dual of the multiplexer. So it makes sense to take up modeling of the decoder now. Moreover, there is one important aspect pertaining to coding style or coding practice for combinational blocks, which needs to be introduced. And I feel decoder will be a good candidate for illustrating this coding practice, which is basically called the default assignment. So we will examine how the decoder is modeled. In fact, we will first examine the wrong way of modeling the decoder, and then we will see how this can be rectified in a very simple and elegant fashion. Coming to the block diagram, we will take up a 2 to 4 decoder. 2 to 4 decoder. So the 2 to 4 decoder will have a 2-bit address, as the name implies, and 4 output lines, say y of 0, y of 1, y of 2, and y of 3. The way I am describing the lines at the output, it must be evident to you that these lines are declared using a single 4-bit vector. And I hope you know how to declare these lines. Of course, I will be including the sample codes also in the description. And I'm also adding one important port called the enable. Now you might be wondering why the enable is needed. The function of the enable is to prevent the uh, decoder from responding to the output, responding to the address when it is deasserted. That means when the enable is 0 or when it is deasserted, whatever be the address, the decoder will not respond. So that is the function of the enable input. Now, why are we providing this enable input? See, in many systems, the address line will be shared by different memories. You know that decoders are primarily used for selecting various peripherals based on an address. So the address bus will be shared between several memory systems. And there will be a lot of switching activity in the address lines rather. Therefore, there may be glitches, there may be switching activities that propagate to the logic inside the decoder and reach the output, unwanted spurious transitions. These transitions may not cause any functional issues, any malfunctioning will not be there. But unwanted transitions in the logic and in the nets will lead to unwanted power dissipation, because for CMOS we know that switching activity will lead to dynamic power dissipation, which means if the transitions in the address line they propagate to the input, then there will be unwanted dynamic power dissipation, which will drain the battery life. So the use of the enable, apart from uh, the functional utility, that is, you can disable a particular memory, that is from the memory addressing perspective. So apart from that, the enable input can be used for preventing spurious transitions in the address line from entering the logic and causing unwanted glitches and unwanted dynamic power dissipation. So the functional role of the enable is to disable and control the access to the system. That is, when you disable this line, the system will not, the memory which is controlled by this decoder will not respond to the address. And the other role is from the point of view of noise and power dissipation. So the decoder will prevent propagation of unwanted or spurious transitions. Unwanted or spurious transitions, so as to avoid glitches and eliminate dynamic power dissipation due to the glitches. Okay, that is as far as the enable is concerned. Now, coming back to the coding part, let us first see how the decoder is modeled in a wrong fashion. So decoder the wrong way. So I'm explicitly discussing this wrong way because naturally the tendency might be to write the behavioral model in this fashion. So let us see what is the wrong way. Again, we start with the always block. So assuming that the output is a vector and the address is also declared as a 2-bit vector, we have two signals at the input, that is the enable and address, which form part of the sensitivity list. Then we know that the decoder will respond to the address only if there is an enable. So we'll describe this as if enable equal to 1, only then you respond to the address. And for the address part, we can use a case because it's only one input, different cases of the same input. So when the address is 0, 0, the output y0 is 1. When the address is 0, 1, the output y1 is 1. When the address is 1, 0, the output y2 is asserted, that is 1. And finally, when the address is 1, 1, the output y3 is asserted. And of course, you may have a default declaration, say y0 is 1, or you can even leave it blank. Okay. So many of us might be tempted to model the decoder in this fashion, and it is wrong. Why is it wrong? It may not be very obvious, but if you look at this code, you can see that we have specified what happens when the enable is asserted. But we have not specified what happens when the enable is deasserted. When the enable is 0, what happens? We have not explicitly mentioned the condition of the outputs when the enable is 0. That is one deficiency. Now the second deficiency is related to the case statement itself. If you look at this case, for instance, if you look at the branch for 0, 0, you can see that the state of the output y0 is specified. Y0 is supposed to be asserted when the address is 0, 0. But what about y1? What about y2? What about y3? None of these signals are specified here. So to sum up, in this code, there are unspecified branches. There are unspecified branches. That is, we are talking about a scenario where several branches of the if statements are left unspecified. Syntactically, there is nothing wrong with this block of code. It will definitely pass the syntax test of a compiler. It will compile perfectly. The trouble is with the synthesis. When the synthesis parses this code, it will determine that there are unspecified branches for the if and case blocks. So how does the synthesizer interpret this? The synthesizer will assign the previous value of these lines for the unspecified branches. That is, you can see here that all the lines y0, y1, y2 and y3 at some point of time, at some branch, they are unspecified. So when there are unspecified branches for a particular output, then the synthesizer assigns the previous value. That means now we are talking about the notion of storage of values. Storage of values. We are talking about storage of values for a combinational circuit, which is not possible, which means there is what is called unintentional latch inference. The value of a particular line can be stored only if we use a latch. Of course, we can use a flip-flop, but here we are not specifying the usage of a clock. Therefore, the synthesizer unintentionally infers a latch for all these lines. That means we end up with 4 latches respectively for y0, y1, y2 and y3. Something that was not intended by the designer in the first place. So for a combinational block, we are ending up with latches, which is wrong. Therefore, this coding style for modeling the decoder is wrong. So what is the alternative? How do we work around this problem? We have a very simple and elegant solution, which is called the default assignment. So the workaround for this problem is the default assignment. And what is the default assignment? See, our problem is there are so many unspecified branches for which there is no value specified for the output lines. So one option will be to enumerate all the branches of the if statement and specify the values for all the output lines, which is possible, but it is cumbersome. It is not recommended, especially when you have so many signals that are to be evaluated for the different if then else conditions. This remedy is going to be really tedious to implement. That is where the default assignment comes in very handy. So what exactly is the default assignment? Let us again rewrite the code. So again, we start with always at enable or address. Begin. Before we get on with the case statement, we make a default assignment. We say that we make a default assignment. We say that y, the vector y, is a 4-bit vector. It is 0. All the 4 lines of y are 0. This is the default assignment. Why are we making this default assignment? We are making this default assignment because if all the branches of the if statement which comes beneath, they evaluate to false, then still we have this default assignment. We are not left with a scenario where there is an unspecified unspecified branch of the if statement or unspecified branch of the case statement. So this single default assignment will take care of all the unspecified if then else branches or case branches. Now we can reproduce the same block that we used earlier. That is, if enable is equal to 1, if enable is equal to 1, we get on with the same case block. It is absolutely the same now. The only difference that we have introduced is the insertion of the default assignment. Now we get on with the same old sequence. For case 0, y0 is 1. Now we don't have a problem here with y1, y2 and y3 because for this case, the default assignment will be taking into effect. Similarly for the other lines. For 1, we just say what happens to y1. We are not bothered about y2 and y3 and y0 because they are taken care of by the default assignment. Similarly for the other two values of the address line. Y2 is 1 and finally for 1, 1, y3 is 1. There you are. Of course, I omitted one thing. When we are having multiple assignments inside a branch of the if statement, we have to demarcate them with begin and end. That's it. So you can see how elegantly we have solved this problem. Just by a single default assignment, all the unspecified branches of the if or case statement, they are taken care of. And we are able to avoid unintentional latch influence. So now let us wrap up the first part of the video on combinational subsystems. Let us try to summarize the important points that we have learned during the course of this lecture. The first point is that combinational subsystems respond to the present combination of the inputs. Combinational subsystems respond to the present, the word present has to be underscored, combination of the inputs. Point 2 relates to the coding practice. While modeling combinational systems using always blocks, it should be kept in mind that all inputs should be included in the sensitivity list. So again, I repeat, it should be kept in mind that all inputs have to be included in the sensitivity list. The reason this is got more to do with simulation. If the sensitivity list is not completely filled with the inputs, then there is a chance that the simulation results will be inconsistent because almost all simulators are event driven simulators, and they use the sensitivity list to determine the events in the various inputs. Therefore, even though the synthesizer ignores the sensitivity list, in order to ensure that the behavioral model and the post synthesis netlist, they simulate identically in terms of behavior, in terms of functionality, we have to ensure that this particular stipulation is adhered to. And point 3 is related to the default assignment statement. So while modeling combinational systems, while modeling combinational circuits or combinational subsystems, if then else blocks should have a default assignment. I'm not talking about the default keyword in the case statement. Here we are talking about the default assignment to be provided before starting the if then else block or the case block for that matter. If then else block should have a default assignment. The reason, this will help completely eliminate unintentional latch inference during synthesis. In case some of the branches of the if statement are left unspecified or incompletely specified. So there you are. These are the 3 points which are the key takeaways from this discussion. So we will wrap up this video now. We will have one more uh, part related to modeling of combinational subsystems, where we will be taking up behavioral models of more typical combinational blocks like arithmetic circuits, priority encoders, and so forth. So we'll wrap up for the time being. We'll meet again in the next video. Thank you.